As you go from 0 to pi over 2, what does our distance from the pole do? It goes from what to what? 1 to 3. So we imagine we're sweeping this way, sweeping around counterclockwise, and as we do that, our radius is going to start at 1 and end up at 3 up here. Do you see that? So we imagine sweeping the angle this way, and as we do that, r just increases to 3. And then from pi over 2 to pi, we're going to sweep around this quadrant, and r is going to go from what to what? 3 back to 1, kind of in a symmetric way. So it looks similar to what we just did. And then, so now it gets a little trickier. As we go from pi to 3 pi over 2, r is going to go from 1, or about a little less than 1, to negative 1. So at 3 pi over 2, here's 3 pi over 2. Where's negative 1? It's up here. So somewhere in there, what happens? The distance from the pole is 0. So as we're sweeping, r is going to get less and less and less until for some angle in between there, you're going to hit the pole. And then as you keep sweeping, now you're going to have negative values of r. So what's that going to look like? We're getting closer and closer to the pole until some angle in between, we're going to hit the pole. So maybe that's this angle right here. Just for sake of sketch, okay? And then for sweeping the rest of the way, we're going increasingly negative values to negative 1. So it's going to go up like that. And then it's going to reverse that, right? So from 3 pi over 2 to 2 pi, it's going to go from negative 1 back to 1. And along the way, it's going to go through the pole and cross over into positive territory again. So it's going to get less and less negative to 0. And then it's going to increase out to 1. Does it make sense? Anybody have a question? Yeah, it's very mechanical, and it takes too long and doesn't require any thought. So yeah, this is a better way to do it, to become fluent. The whole point is to see how those two quantities are changing together, how the angle measure and the distance from the pole are changing together. That's what we want to focus on. And so by doing it like one interval at a time, that forces your mind to think that way. Other questions on this? Requests?
Well, can we go over the equation of that one?
Oh, this first one? Okay, so the equation midline is 1. So whatever it is, we're going to add 1, because the midline's at 1. And then what's our amplitude? 2. So it's going to be 2 times something. And we're starting at the midline and going up. Is that sine or cosine? That's sine. And so then, do we have a period change, right? So is this sine some period other than 2 pi? No, it's 2 pi. So therefore, 2 sine theta plus 1.
I think 5a has shift and
No, you can write them all without a horizontal shift.
5a.
Oh, does it?
5a. Looks like it's both.
So instead of you don't want to do a horizontal shift. You want to do the opposite of cosine here, right? So if you just take the negative of cosine, you don't have to do a horizontal shift. Do you see that? Because it's just cosine flipped over the midline. That's the way to go. But for later in class, we're going to work more. Whoa. Okay, so later in class, we're going to work more on this fourth one. So we want to find out, where does it cross the pole? For what angle does it cross the pole? Remember in the third and fourth quadrants, there was a place where r was 0, right? So right here. So we want to figure out where is that. So how would we do that? So this is our r as a function of theta, and we want r to be what? 0. So we're going to do 0 equals 2 sine theta plus 1. And so we're going to get sine theta equals negative 1/2 when we solve for sine theta. So you need to know your unit circle. Where is sine theta negative 1/2? For what angles? Who remembers?
210.
From or south
So it's just a little bit further than pi. So that is 7 pi over 6. And then almost 2 pi is where you hit a y coordinate of negative 1/2. So that's from remembering your unit circle. So those are those angles theta. So it's actually, so where's that? Here? No, it's not. Just kidding. Is it one more down? It's one more down. Sorry. So 7 pi over 6 is this blue one here. 11 pi over 6 is this blue one here. When you're sweeping around and you reach that angle, that's where your graph is going to go through the pole. R is 0. So before that angle, remember it's positive. And then at that angle is when you cross over into negative territory, and now you're back in the first quadrant for these angles here, right? For these angles here, R is negative, so you're back in the first quadrant. Okay, so remember that. So when we come back to this, we found that it crosses the pole at 7 pi over 6 and 11 pi over 6. Okay. So request of 5 and 6. Is there one of those we want to do? Maybe. Okay, so 7's a definite. How about 5 or 6? 5. Okay, so 5 starts. So again, we can go by pi over 2 here. This one seems pretty easy here. We can just go by pi over 2 at a time. So as you go from 0 to pi over 2, R goes from what to what? 1 to 3. So you imagine sweeping your angle, right? Counterclockwise, and as you do that, R just keeps increasing to 3. So you have to think radially this way, right? You're thinking about the angle increasing, and as you do that, you're getting farther and farther out away from the pole, and then back to 1. And then what happens? From pi to 3 pi over 2, it goes to 3. And then back to 1. And then it just repeats. Peanut. So then I just keep doing that. Okay, so then the function. So midline's 2. And the period is, now the period is half as long. The period is pi now. So what will give us a period of pi? Cosine of 2 theta, but then it's flipped over, the midline. So you could do 2 minus, this is 2 minus cosine 2 theta, or negative cosine 2 theta plus 2, the R of theta for this one. Okay, and I heard 7, so we'll do 7. All right, so let's go. It looks like, again, so this has a period of 2 pi. So once we get to 2 pi, it's just going to repeat. So every pi over 2, we'll do every pi over 2. Oh, this is 6. 7. There we go. Oh, yeah, good one. Okay, so let's go every pi over 2. Every pi over 2. In the first pi over 2, R goes from 2 to 0. Okay, so it's going to be 2. You imagine the angle turning this way, and R is getting less and less and less and less and less and less and less to get to 0. And then, now we're in negative territory. From pi over 2 to pi, we're going to go from 0 to negative 1. So where is negative 1 at this angle measure pi? Back here. And so as soon as we start doing these angles, it's negative and increasing out to negative 1. And then from pi to 3 pi over 2, it goes from negative 1 to 0. Okay, so at pi, it's negative 1. At 3 pi over 2, it's 0. And it's always negative. So it's in getting closer to 0, so like this. And then from 3 pi over 2 to 2 pi, essentially from 0 to 2. So that's this last quadrant here, from 0 to 2. Does it repeat from there? No. Now at 2 pi, it starts going farther away from the pole. So from 2 pi to the next quarter circle, now it goes out from 2 to 4. See that? So now it's going to, you imagine, you're rotating through here, and it's just going to get greater and greater and greater and greater and greater and greater till it gets to 4. And then at 3 pi, it keeps getting greater till it reaches 5. So it's increasing from 4 to 5. And then it goes back to, at here, it's back to 4. And then at 4 pi, it's back to 2. And then it starts over. So lots of loops here. Okay, questions? Does it make sense? So this is really, you really got to understand how the negative r's work and how the distance from the pole is changing as your angle is changing, right? You're sweeping around counterclockwise and you're varying your distance from the pole as you do that. Questions on that one? You got to do this for the final. You got to do this for the final, this kind of stuff. If you can do this, you understand polar coordinates. This is to see if you really understand what's going on. Questions on this one? Equation, okay. Looks like the period, so our midline is 2 again, plus 2. Looks like we got negative cosine. What is the amplitude? 3, so negative 3 cosine. What is our period? Now our period's 3 pi. Thanks, negative sign, you're right. Starting at the midline and going down. So negative sign. And it doesn't repeat, right, it repeats at 4 pi. So we need this to be 2 pi when theta is 4 pi. So when our input reaches 4 pi, we need that whole expression to be 2 pi so we get one cycle. So B is going to be 1/2 theta. Yeah.
Is it okay if you check those on a calculator once we get the equation?
Sure. Yeah.
So like if you graph that in polar form of rectangle form, it should be the same graph.
Which should?
So like if you graph that equation in polar mode and rectangular mode, it'll give you the graph.
Yeah, it should give you those graphs. But I don't remember the test, but there could be a no calculator portion on the test. You got to know how to do this by hand. Yeah. Yeah, I think in this final, there's part of it you get a calculator, part of it you don't. Okay?
And my calculator only gave me this.
Because you didn't show enough theta. So if you only show 0 to 2 pi, then you only get that little part there. Right? So you need from 2 pi to 4 pi, you get more different part of the curve. So if your theta is just set from 0 to 2 pi, it's just going to graph that much of it. Yeah. Yes, sir. Yeah. Okay, fast. I'm going to go fast. Ooh, this is hard. All right. This is harder. Okay, so start at -1. So when 0, you're at -1. And then right away, it's going to get back to 0. So really fast, it's going to get to 0. And then you're going to have a little, this is pi over 2. This is too hard, don't worry about this. This is real hard. Okay, so at pi over 2, it's -3, so you're here. So basically, it's going to do this. You're going to have a little loop, and then it's going to go down like that. And that's all from 0 to pi over 2. Does someone get that? All right, and then you're going to go from -3 back to 0. So pi. So I think then you get.
It's like a wild. Yeah, it's like a little flower.
Does it go? It goes to 1. This was -1, so it goes back to 1, right? Is that right? Let's see. So a little 1, and then out to what did I say, -3. All right, and then back from -3 to 0 to 1. There's to 1, then back to 0. Oh no! I see. To 1 like here, then back to 0, and then starts going negative a little bit until it gets out to -3 at -3 at up here. This one's hard. It just takes I'm trying to do it fast, and it takes more thinking than that. You really got to think through this one. So this is not worth spending the class time on. That would be a better one to do, but let's just go on to other stuff. So you got now you've got a more basis to work on these. Okay, the ones that we didn't do. 8 is a challenge. That's a true challenge. Okay. All right. So. Let's look at, we never did 6.
Look at this. 3 pages.
Oh, that's here, okay.
I write big, really terrible notes. When there's open space, I guess.
Okay, number 6. So number 6 is a very attainable one. You should be able to graph this one on your own. I'll do it fast. So number 6 starts at 0 and goes out to 2. And then continues to increase to 4 at pi. And then back to 2 at 3 pi over 2. And then back to 0 at 2 pi. And what's the equation of the graph? -2 cosine theta plus 2. Midline is 2. It's the flip of the cosine. It has the standard period of 2 pi, and the amplitude is 2. Okay, so now what I'm interested in is I want to know what is the slope of the tangent line right there. So yes, derivative. So what if I want the slope of that tangent line? What derivative am I after? I want to know. Well, but what the derivative of what with respect to what? So we've got x, y, r, and theta. We got 4 different quantities. If I want the slope of that tangent line, it'd be d what? D what? It'd be dy slope dx. So it's like we're superimposing the xy plane onto the polar plane, and we want to know what the slope is, right? What's the change in y for the change in x? Okay? And so in order to get, but we have, what do we have? We have everything in terms of r and theta. So to do this, dy dx equals dy, what? D theta over dx d theta. Okay, so what is y in terms of theta? We have r in terms of theta, but what's y in terms of theta? R sine theta, right? We know that from our conversions. And what is x? R cosine theta. And what is r? Well, r changes. R is a function of theta. It's this function of theta. This is our r. That's r for our graph. You see? Because r is negative 2 cosine theta plus 2. So we can rewrite r as negative 2 cosine theta plus 2 times sine theta. And what's our r cosine theta? It's going to be negative 2 cosine plus 2 times cosine theta. So now we're ready to do dy d theta. But let's just do it generically first, okay? So we'll just do it generically first using our just any r function. But remembering that r is a function of theta, right? So how do we take the derivative of this function of theta, r of theta, times sine of theta? What will we need? Product rule, right? Because r is a function of theta times sine theta. So it's going to be first times the derivative of the second plus derivative of the first times the second. That is dy d theta. And then this is r of theta. Okay, so this is our function r of theta. And then dx d theta is r of theta first times the derivative of the second, negative sine theta, plus derivative of the first times the second. So this is our, for any r of theta function, this is what dy dx is, the slope of the curve, of the polar curve. That's a generic formula that will be true no matter what r of theta function we have. Right, but we're going to have to do the math for r's, right? Yes, you're correct. That's right. Okay, so for r's, what is it? R of theta is, so we're going to just follow what we did here on that product rule. R of theta is negative 2 cosine theta plus 2 times cos theta plus r prime. What is r prime? So we got to do the derivative of this, which will be 2 sine theta times sine theta. All over. That's times r theta, negative 2 cosine theta plus 2. Negative sine theta plus r prime is still 2 sine theta cosine theta. Okay, before you plug in your value, so what value are we going to plug in if we want the slope of the tangent line right here? Pi over 2. So our theta, the theta that we want, so to get this particular slope, now we want dy dx evaluated at pi over 2. Before you do that, see if any of this will simplify and crunch down a little bit. Maybe on this one it won't, but on some of them they do, and you get lots of cancellations. But now for pi over 2, what is the sine and what is the cosine of pi over 2? The sine is 1. So sine of pi over 2 is 1. Cosine of pi over 2 is? Okay, so for this particular case, looking at pi over 2, we don't want to bother simplifying. Why? Because any place there's a cosine theta is going to be 0 for us wanting it at pi over 2. See that? Now, at any other angle, we can't do that. But this is going to simplify things greatly. Anywhere there's a cosine theta, boom, it's going to be gone because cosine of pi over 2 is 0. So, gone, gone. Again, this is only because we're evaluating at pi over 2. Okay? This is because we're evaluating the derivative at pi over 2. So that whole thing is 0. That's gone. The top is 2 sine squared, which is 2. Sine of pi over 2 is 1, so we get 2 in the numerator. Denominator is? Negative 2. Nope. This is plus. This is plus. Negative 2 and sine theta is? So negative 2. Therefore, slope is? Negative. Doesn't make sense. That's negative 1. Well, my sketch isn't great, but it should be doing this. It should be reaching up a lot higher here. More like a circle. And like what it's done here. So then that just told us that the slope there is negative 1 at that point. So then the equation of that line, so we can do the equation of that line, we can do it in xy. And so we just need, what is that y-intercept right there? So at pi over 2, we're at a radius of, or an r value of 2. So what xy point is that? 0, 2, right? In xy. So if we've got through the point 0, 2 with a slope of negative 1. That should be an easy line to write the equation of, right? What's negative x plus 2, right? That's the y-intercept, 2. So we just do y equals negative x plus 2. Okay, could we write that equation of that line in polar coordinates? Could we write the equation of that line in polar coordinates? How would we do it? So we need to get what involved here? Yeah, we need to get rid of our y and x and get our, I'll do that in blue over here on the graph. I don't need this graph anymore. So in blue over here, we're going to change this equation of the line in Cartesian coordinates. Y equals negative x plus 2, and we're going to change it into polar coordinates. Y equals? R sine theta. X equals? And what is a polar function? What as a function of what? R is a function of theta. So we want to gather our r's together and get the r by itself. So we have r sine theta plus r cosine theta equals 2. Factor out the r. R equals? Right. So r as a function of theta, this line, 2 over sine theta plus cosine theta. So notice that equation is like not very friendly, right? 2 over sine plus cosine. Why is that? Because we're trying to we're making a line in polar coordinates, right? A line in polar coordinates that's going through the polar plane like that. It's not suited to the polar plane because the polar plane is all about how far away you are as you change angle. So doing a line like that diagonally through the polar plane is just it's like a foreigner in a strange land. Okay, it's like a foreigner in a strange land. So its equation is going to be something kind of unconventional or not kind of friendly. This awful fraction with sine and cosine in the denominator. Yes, sir.
Is there ever a case where you superimpose Cartesian polar plane?
That's what we're doing. Yeah, because we found we to get the slope of this line, we're doing dy dx. So that's exactly what we're doing. This is the point 0, 2 in the Cartesian plane. And it's the point, pi, or 2 pi over 2 in the polar plane. And then we found the equation of the line in Cartesian coordinates right here in the polar plane. And now we've got its polar equation. So that's exactly what we're doing in this problem.
Is that a common thing in application?
In application, I'm not sure. Okay, so what do we introduce? We introduce derivative, right? Rate of change, dy dx is dy d theta over dx d theta. Yes, sir?
This is like basically doing very big triangles with x and y distances from the pole.
What's that now?
Like if you were to get like any point to find the distance, you would do like a triangle.
You on that line, you mean?
Yeah.
On that line?
Yeah. Find distance.
Kind of. Yeah, so, yeah, it's just weird, right? It's just weird to have a diagonal line through the polar plane. That's why you get a weird formula. That's the the layman's version of that. Okay, so we got to do area. Okay, we got to do area now. Oh, so then if you wanted to find the points where you got a vertical tangent, what derivative would you look at? You wanted a vertical tangent to the curve. What derivative would you look at, and what would you do? You want a vertical tangent.
dx
Dx
over d theta.
d theta. You're going to look for dx d theta. As theta changes, you want, for a small change in theta, you want x to not change, right? If x doesn't change, then you have a vertical tangent. And then, so if we want it to not change, we want dx d theta to be 0. So if you want a vertical tangent, you're going to set dx d theta equal to 0. If you want a horizontal tangent, you're going to set dy d theta equal to 0. Okay, so that's similar to our parametric problems that we did. So if you're looking for these, say that the very highest point, if you want the maximum point or the minimum point of this, it's called a cardioid. It looks like a heart, kind of. All right, if you want the very highest and very lowest point, are you going to look at dx d theta or dy d theta? Highest and lowest. dy d theta equals 0, right? For a change in theta, you want no change in y. That's dy d theta, dx d theta would be to get the highest and lowest point or the horizontal tangents. So make sure you write that down. We're not going to do an example of it. It's similar to what you did before with parametric. Okay, area. Questions on derivatives? Okay, so area. So we have, the first thing with area is we have a little setup here. If you have an angle, say alpha, and a radius of r, what is the length of that arc right there? So, r. So s is the arc length. How do we calculate that arc length? S equals, yeah, if alpha is in radian measure, then that arc length is simply r times alpha. Alpha has to be in radians. Okay, so that's a little setup that we're going to need here in a second. Okay, so we've got this function. We've got some function, r is a function of theta like this. It can be anything, like the ones we've been sketching. and we're interested in from some starting angle to some finishing angle. And so like when we did integrals in x and y, it was like all the area from the curve from the y coordinate down to the x-axis. But now if r is a function of theta, what's that going to mean? R is a function of theta. It's going to be like all the area from the curve to into the pole, right? So it's going to be this region right here that we're interested in. So as we sweep from theta 1 to theta 2, how much area is there from R down into the pole? That's analogous to from the y coordinate down to the x-axis. So what are we going to do? We're going to take a sliver, a little change in, right, a typical slice, right, a typical slice, where this is our d theta. And we want to get the area of a typical slice. So this, all this area right here in our typical slice. And we're going to use the equation of a triangle. Equation of a triangle. Area is, so a little bit of area is going to be 1/2 base times height. So what's the base? The base of our triangle is going to be this little bit of arc length. This little bit of arc length right here, and that's what we get from this. So what is that arc length? R d theta, right? So the change in the angle is d theta, and we're a distance of r away. So that base right there is going to be r d theta. And then what's the height of the triangle? The height is then from the pole out to the curve. And what's that? What's that distance? R. So we got it. So a little chunk of area is 1/2. This should be delta r squared. There's our typical, based on the area of a triangle, that's our typical wedge of area for a angle change of delta theta. So then we're going to integrate. We're going to sum up all the typical little pieces from theta 1 to theta 2. And each typical little triangle is 1/2 r squared d theta. Right? Again, this is the area of a triangle, right? That's 1/2 base times height. So that's going to be our area from the curve into the pole. So it's going to be all, so this area is, I'll do it in red, is giving all this area here. And we need little typical slices. Why? Because as you change, as d theta changes, r changes, right? R, the distance from the pole, is constantly changing. So we need a bunch of sliver triangles to get all those different distances r away from the pole. That's why we need to integrate. Okay, so let's go back to that. Any questions on that derivation? So that's our area of a wedge in there. Okay, so let's go back to our...
How did you get the base as being RD?
Yeah, I was gonna say the question.
Because it's like the arc length, right? And so that we said the arc length was the angle measure times the radius from that very first thing I did.
Yeah.
So that it's r times delta theta.
Okay.
Yeah.
So in application to that, the r squared will be replaced by the function that we would have squared.
Yeah, so r is a function of theta, right? So a is integral of theta 1 to theta 2, 1/2. It's r of theta squared. Because r is changing. As theta changes, it's a function of theta. So yeah, and we're doing d theta, so that expression will be in terms of theta. Yep. Okay, so what was the one we did? I told you to remember with this one that had the loop in it, that I said remember the angles? Sure. Okay, it goes up to 3.
Which one was that? Number 4?
Goes to 1, darn it.
7 pi over 6, right?
And so then at this angle right here,
You said it was 7 pi over 6, not that.
yep, it's where it hits the pole, and then it makes a loop to -1. Something like that. Okay, so what would we get if we did the integral from 0 to pi over 2 of 1/2. What function was this again?
2 sine theta plus 1.
What area would that give us? So what area would that give us?
Right side of the function.
So, okay. Yep, it's on the right side. So 0, so I'll do it in red here. 0, angle 0 is here, like this. So that would be the starting angle. And then we would sweep to pi over 2. So it would be that right there. So then what area are we going to get? So the loop it is not even existent from 0 to pi over 2. So you can just ignore the loop, right? So what are we going to get? It's going to start here. We're going to get all of this area right here. So it looks like a D. Do you see that? It kind of looks like a D with a flat bottom. That's the area it's going to calculate. That integral right there. So then with this, we're asking then, what's the area of the loop? So what is the area inside the loop? How are we going to do it? Question?
So you could be from pi to wherever it crosses the other pole.
Well, so again, for what angle does the loop start?
7 pi over 6. 7 pi over 6.
So we found it's 7 pi over 6. And then where does the loop end? 11 pi over 6. So if we want the area of the loop, that's going to be from 7 pi over 6 to 11 pi over 6. And it's going to be 1/2. It's just going to be the function, because that function gives us the loop. And look, we don't have to worry about it being negative or positive. Why? Because r gets squared, right? So that the thing that we're differentiating is squared. So we don't have to worry about signs. That r is always negative in that loop, right? The loop is this part of the graph right here. Gives us the loop. And r is always negative. We don't have to worry about it because the formula for the area gives us a square. Squares it. Okay, yes sir?
So like the area within that little circle is counted twice in that one because it's different from that one.
Yeah, so this one has no idea about this part of the curve here. And this first one has no idea about the loop. It's only this, so from 0 to pi over 2, you just get this part of the curve right here. It has no idea about the loop existing. And when you get to the loop, it has no idea about the rest of the curve existing. It just knows itself that much. Does that make sense?
So if you get the whole thing,
What's that?
what's the period that says? So you'd have to do to get the whole thing.
Okay, so what would happen if you did the whole thing? If you did the whole thing,
If you did the whole thing, it'd be like in the area of
yeah,
the XY line.
yeah, you'd get everything inside. So you would be counting that area twice, It would sum up. It would be twice that loop because that would all be included when you did everything else, right? So you'd get everything inside the external curve, and then this would get counted twice. Yes, sir. So if you wanted just the area outside the loop and inside the cardioid, then you'd have to take the integral from 0 to, yeah, you'd have to take the whole thing, and then you'd have to subtract out the loop. Subtract out the loop, yeah.
So like if you were trying to do like the area for the XY graph without having to stop and change to make sure that you get to not adding like any variables, you should just do the polar one.
But you'd need the polar equation of your curve in x and y. Yeah.
Just for clarification, 0 to pi over 2 is for the larger loop.
0 to pi over 2 is this curve right here. That's 0 to pi over 2. That's the curve you get. So it's going to be from 0 to pi over 2. It's this right here. That shape. That red D. You see that? It has no idea the loop exists.
So there's technically like 3 integrals you have to do to find the area of that whole shape. Like of that one part, and then what about the bottom part? Is that bottom negative? So I'm just wondering how you find the area of the whole figure.
Okay, the whole figure. You'd have to go from 0 to 7 pi over 6, and then from 11 pi over 6 to 2 pi, and that would give you this little part here. And then you'd have to subtract this one if you wanted everything outside the loop and inside the cardioid. But if you just wanted everything inside the cardioid and you just want to count the loop once, then you do those two integrals. You'd go from 0 to 7 pi over 6 and 11 pi over 6 to 2 pi, and that would give you all of this area inside that thing and the loop just once. Yeah.
So does that mean there's no such thing as like negative area, like we got in Cartesian?
Right, because when r goes negative, you're taking integral of a positive value because this thing gets squared. This thing gets squared, so it doesn't subtract it out automatically.
So that's it. 0 to 7, 2 pi 6, 1 pi 6, 2 pi. This is already counting. That's it.
One more quick note. Okay, one more quick note. What's the equation of the blue circle in polar coordinates? No, in polar coordinates.
R equals 3.
It's just all, for every angle, r equals 3. Okay? And then for this one, it's similar to the example we did last time. Center 0, 2. Or center 2, 0. Radius 2. That's actually going to be 2 cosine theta. I think. 4 cosine theta. So what if we wanted, okay, just look. What if we wanted, this last thing. What if we wanted all this area here? I'll do it in red. Say I want the red area. What would I need to do? How would I get that red area? Here's the key. It's defined by the blue curve until the intersection point, right? So we start at theta equals 0 and start sweeping. The area is defined by the blue curve up until that intersection point. And then when theta surpasses that, then that area is defined by the black curve. 2 integrals, right? You're going to add this first integral for the blue equation. And then you're going to add on, now starting at that angle theta, say theta 1, you're going to add on from theta 1 to whatever that angle theta is, and add the two sides together. Because you're defined by the blue curve up to theta 1, and then you're defined by the black curve down back to when it gets to the pole. So to get that, you have to add, you recognize that you have to add integrals. One for each curve.
So enough to write integral for the blue one. How do you write the integral for the black? Because that's not touching the middle.
What's that?
I don't get the second part.
First of all, is it 4 cosine theta? Is that right?
The first half makes sense. It's like,
The second part would be like going from this angle, this angle.
Wait, Rudy, what were you saying?
So going from like this angle to this angle. So like let's say that's like 60 to 90 degrees. And that's the only part that's covered up by this.
Okay, I was right. That's right.
What? No, that's adding. It's like the first one you take the area of the blue one for this area right here.
you do this. You take this one.
So that one, I get the black one.
So this is 2, 0, radius 2. Good. Okay, I got it.
This part is this right here.
So the first thing we have to do is find that angle where it changes. So where's that angle? Well, that's where r's are equal, right? So 4 cosine theta has to equal 3. See that? So we're saying cosine theta equals 3/4, which is not one of our key angles. So it's the arc cosine of 3/4. We'll just leave it like that. We don't. That's fine. Just leave it like that. So this angle is the arc cosine of 3/4.
So with the like the beginning of the end point of the last integral would be at 2.
We'd have to confirm that. Okay, we'd have to confirm that. But so we're going to go from 0 to
The intersection point.
cosine inverse of 3/4 and integrate r. So it's going to be, that's going to be the blue one. It's going to be 1/2 3 squared d theta from 0 to cosine inverse 3/4. Okay? Then plus the black one. Integral from cosine inverse of 3/4, and now you're asking till where, right? So where does this thing get to 0? So I'm thinking about 4 cosine theta, pi over 2, right? At pi over 2, it returns to 0. It goes from 4 to 0 at pi over 2. So it's going to be from cosine inverse 3/4 to pi over 2 of, what, 1/2 4 cosine theta squared d theta. And you're going to add those two together, and that'll give you the red area.
It's like the continuation of the angle.
Yeah, the area, the angle just continues from cosine inverse of 3/4 to pi over 2, but now it's defining the area is the black curve, which is the 4 cosine theta curve.
Right. So why doesn't that calculate the area of like this part of the black?
Because it's not basing off x, it's basing off the low angles.
So remember, you're sweeping angle. So you start with 0, and we're going to sweep, and as we sweep, we're sweeping. It's only the blue curve, right? We're sweeping up like this, and so using the blue curve, we're going to get all of this, like, just think of it radially. We're going to get all this like this.
Right.
But here, we don't want to use the blue curve anymore, because if we use the blue curve, we'll get all this stuff up here. So starting here now, we want to use the black curve and come in, right? So now, starting at that point, now we're going to use the black curve until we get to pi over 2.
Like remember these lines, like the strips are not vertical, they're following the angle.
Okay.
So yeah, so then that's the black. So then starting at that angle, then just think radially, right? Think radially down to the pole. Like this. So you got to think of these areas as extending out radially from the pole. As you rotate through, it's like triangles, right? Triangles on an angle, at the angle of the question.
Right.
So boom, 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 boom. And then now the black curve takes over. Boom, 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 boom to pi over 2.
Gotcha. But that one's based off of the top. You're saying.
That's the break point. That's where we stop. We stop using the blue curve to be the end of it. And now we start using the black curve to be it. So you got to think angle sweeping this way. You're using the blue curve, using the blue curve. Now when they intersect, now we're using the black curve, using the black curve, using the black curve, using the black curve.
Right. But I was just wondering, because like the blue one uses the middle. So like, how come this one's not based off the middle of that certain? How come it's based off this?
Because these integrals always are from the pole out to the curve R. Those triangles, the typical triangles are always from the pole out to R.
Okay.
Always from the pole out to R, right? So starting at the pole, out to R, out to R, out to R. So just think of triangular strips, angular strips.
Yeah.
Okay? And then it starts starting at that point, it's still triangular strips, starting at the pole, but now terminating at the black curve.
Gotcha.
Little triangular strips, all the way to pi over 2.
Uh-huh.
So then the sum of those two will give you that total
Okay.
area.
Yeah, that makes sense. So what would happen if that wasn't on the pole then? Like, if both of them were moved over to the right?
Well, then you have to subtract. So now you're talking about subtracting areas. Because if something's not at the pole and you want something away from the pole, then it's going to be, so all these areas are always to the pole. So you have to subtract out the interior
Gotcha.
from the whole thing.
Okay. So it would be like part of your integral at the beginning. So it would be like.
So if you want, I don't know. If you want this area here,
Yeah.
and this is R1, and this is R2, then it's going to be all the area defined by R2 to the pole minus all the area defined by R1 to the pole.
Okay.
It's always relative to the pole.
Okay. So the pole is key.
Yeah, because your typical triangles in these integrals will have a corner at the pole always. So if you want an area like that, you've got to use subtraction.